to stage to Wolfgang De Salvador and Paul Edwards. They're from Azure Storage and Azure HPC and AI Customer Solutions Innovation. And they will talk about running AI training at the scale, bridging the gap between traditional HPC infrastructure and cloud-native solutions.
Hi, Wolfgang and I, we're from the engineering side of Azure, and we've had the opportunity to support and collaborate with a wide range of customers. These range from startups to large enterprises. And today we're going to share some of the learnings. So if we just go over the agenda, so after a brief introduction, I'll talk about AI training and how it compares to traditional HPC. We'll look at workload orchestration on Azure, and then I'll pass over to Wolfgang, who'll talk about cloud storage, observability and monitoring, and look at conclusion of future trends. So if we start looking at the AI model's lifecycle, so there's 3 real stages in terms of the training. You create your model, you might do some fine-tuning on it, and then you'll be doing your inferencing. And our focus today is on the training, large-scale distributed training, and this is when the customers are running, say, hundreds to thousands of GPUs per job. So this slide shows all the AI services that Azure has to offer. Many customers can just use one of these services, but when it comes to the large-scale training, then we need to go down to the AI infrastructure, and so we'll have the GPU, storage, and networking, and then we'll have something to orchestrate it. So I'm sure we're all familiar with this. We'll start with HPC. What makes up HPC? We have our compute, we have our high-performance SKUs, CPUs with GPU accelerated and delivering the high performance. There's some sort of high-performance storage, shared storage generally, high bandwidth, and IOPS and low latencies. And then the interconnect. So we'll have extreme bandwidth and very low latencies. And so this is the HPC recipe. And this graph here shows the flops required for notable AI models. And each year we have more powerful new models. And so since 2010, we've had a 4.6x year-on-year growth. So let's look at going from HPC to AI training. So with application management, I've put here a limited subset of software installed in a shared cluster folder, but of course that could be easy or CERN, VM, FS. But for AI workloads, then AI training, then they're almost always distributed as containers. There's thousands of packages, and they're many gigabytes in size. And so this even presents challenges even starting up. And then we've got new data sources. There's vast amounts of data, continuous ingestion, and different stages of the training. So when we look at a multi-node container run, then the containers need access to these specialized network devices and accelerators, and they need some sort of topological awareness. They need to establish communication awareness and who's part of the job for startup. And then they need to be spun up synchronously because there's often timeouts with starting up, and you don't want to take too long starting up because you're wasting your GPU resource. So in terms of the storage and compute requirements, then, we'll have the initial ingestion and what happens downstream when you have your model, but for the actual training, then there's some sort of data preparation. And on the cloud, then we can do this on some sort of general purpose hardware. And for training, then during training, then we need to do checkpoints, reading when starting and writing throughout the job. And so we want to do this as quickly as possible because we want to maximize the GPU usage because they're the expensive part of the resource. So with the customers that we work with, and there's typically two types of organizations. We have our HPC native organizations, and they come from HPC. They have their traditional HPC schedulers. They'll have a shared file system, low latency, high bandwidth. Of course, you'll have your IB or high-speed interconnect. But then for the containerization, then they'll have to have something built into the schedulers, into the traditional schedulers. And then the other type of customer is the digital native organizations, and they're usually leveraging some AI workflow manager or doing some scheduling themselves, so they don't really have a strict preference there. They're also more likely to embrace cloud storage from the start. It's often new projects. They'll still need the InfiniBand for when they're running their large scale, but they're more likely to be adopting a container native solution. So moving on to orchestration in the cloud. So at the lowest level, then there's virtual machines. You could just provision lots of virtual machines. We do have customers doing this. And then basically you're managing your entire stack yourself. And so when customers do this, they could be installing, say, a Slurm scheduler, or they might be running their own Kubernetes. But we also have Azure Cycle Cloud, which is our HPC orchestrator. It can create HPC clusters and dynamically scale based on scheduler load. And then going more cloud native, then there's Azure Kubernetes Service. So it's containerized native environment, and it's, customers, I think, like it for it's being cloud agnostic. So I'll just tell you more about Cycle Cloud. So Cycle Cloud itself is software. It's deployed on a VM. It creates a web-based portal, and from that portal you can then create clusters. So in the diagram here, then it would be creating, say, the Slurm head node and the GPU nodes and general purpose nodes. These would be presented as queues in Slurm, and they would automatically scale as you add more jobs to the Slurm queue. It's also configurable, so you can easily add mounts to your compute node, so you can put in your Lustre file system for scratch storage. You could use NetApp for home directories. But what we also have now as well is Cycle Cloud Slurm workspaces, and that actually creates, as well as your Cycle Cloud virtual machine all set up, it will create your first Slurm cluster, and it will give you options to have your Lustre file system and something for your home directories too. And in fact, we've even got an option for open on demand now. This is just a plug for our, Wolfgang and I have been working on a GitHub repo. We're looking at creating some end-to-end workflows running AI training. So we've currently got Megatron LM and an example with LLM Foundry. And this uses Cycle Cloud Workspace with Slurm, and we've got in the GitHub repo, we do explain how we, like the steps through to actually creating it, which is very simple. It's a few lines with the CLI. And what this gives you is we have the Azure HPC images, we've got Slurm set up, it's automatically scaling. For the containers, then we use, we've got Pixus and Enroute, and again, this is Cycle Cloud's Workspace with Slurm, it automatically installs it for you. And so we can run any training stack. And so if you're interested, just check out the GitHub repo. And then so the other thing, say what customers would use for the large-scale training is Kubernetes. And so if someone coming from HPC using Kubernetes, then the first things they'll sort of notice is the scheduling. I mean, when you want to do a large-scale multi-node job, then it doesn't have gang scheduling by default. So it is missing some features there. I mean, and the way Kubernetes is supposed to be abstracting away your hardware, but you do need access to your device drivers and also topology awareness. So for customers using Kubernetes, then For the device plugins, then there are GPU operators and network operators by NVIDIA and AMD, so they can give you access to the devices. For the scheduling, then to get topology awareness and scheduling policies, then there are third-party schedulers such as Volcano and Q. And if you want something on top of that, then workflow managers such as Kubeflow or Ray can be used. And then, that will be there to run, say, your PyTorch jobs or TensorFlow jobs. And I'll pass over to Wolfgang now.
Thank you so much, Paul. So let's say, as Paul mentioned, between a classical HPC infrastructure and more cloud-native infrastructure, there is a changing paradigm in orchestration, there is a changing paradigm on how configuration are managed, and this impacts unavoidably also the storage paradigm somehow. So coming from an HPC background, we are used basically to have to conceive the storage, and this is something that in several cases, as we will see, keeps happening in AI training with the standard HPC paradigm. So having tier storage like a scratch area and a project area, or eventually even a third area for long-term retention. Having, in terms of access and protocol, something very HPC specific, so having basically access base on a network mount with low latency, with protocols that are usually very, very sensitive to latency, like NFS, Lustre, BGFS, and finally also to have a fixed size storage. Going into the direction of a more cloud-native approach, if we want, we move in all these layers to a different logic. So being able to have a performance and scale that can be fine-tuned for the specific needs, having access that is now more based, for example, in the case of object storage, on managed identity solution or centralized identity solution, and in terms of protocols going to using APIs, eventually with TLS encryption, and also in terms of cost, having the possibility to scale both in size and performance dynamically. So if we want, there is kind of a gap between these two domains, and at the moment, as we will see, there are two ways through which this gap is kind of bridged, meaning so allowing to plug a cloud-native storage model inside AI training in an easy way that are mainly fuse drivers and the use of storage accelerator. And we will talk about both in a minute. So basically, if we look at the concept of storage accelerator, basically, if you look at a classical on-premises storage deployment, there are two main areas. There is the scratch area with the live data where there is direct I/O from the compute resources that is performed, and the project area. Eventually, in some cases, there is also a third tier, which is an archive area. And of course, the performance and cost balance between the three areas changes accordingly. This is, if we want, is the classical HPC way of conceiving storage, typical of an on-premises system. Let's say that what we see more and more happening in the cloud is switching to a paradigm where we have a core storage layer that usually is an object storage that is able to basically store all the data asset of a specific organization or eventually a project, and then having scenario where the compute nodes can access this core storage layer using accelerator, so a storage solution that can do kind of a caching of the namespace of the core storage layer, or eventually, if it is possible, and we will see that, directly interacting from compute nodes with this core storage layer. All of this for the best TCO, for the best performance, but also at the same time to have a transparent namespace between all the things. Let's say that if we look at a classical way of doing AI training, and that can be applied also in the cloud, we have a first phase where there is just a parallel file system for all the different phases. For data loading, then there are the training phases, and then there is the checkpoint right to the parallel file system. And usually, the parallel file system bandwidth is dimensioned to get the checkpoint done in the minimum time possible so that the GPU can then start again for the next iteration without losing any expensive CPU seconds or minutes in this case. But in this traditional storage model, we can plug in the concept of having a core and accelerator layer. So mainly, without changing the workflow at all, so with the same concept of the previous slide, having a direct connection. Here there is an Azure example with Azure Managed Cluster and Azure NetApp File and Blob Storage, having the possibility to see and to be able to visualize with a transparent namespace both the domain with the fast performance of the accelerator layer, but with all the data that are in the core layer. This, if we want, is a way to bridge the gap in one way, but it's important also to say that there are also scenarios where directly the GPU nodes may access directly the object storage, and they may be able basically to directly be used for data loading, for training, and also for checkpointing. And also the object storage themselves provide possibility. This is something that has been presented at Build 2025, where a scaled storage account that is basically created pairing physically below the same logical account, multiple hardware and network from a storage standpoint perspective, allows to reach very large bandwidth. So through a fuse driver and through proper casing, this can be leveraged. We don't have the time to show you the demo. This will be a video. However, if you look at this video, that I don't think it will be starting, but we can provide you the link afterwards. It's shown how a blob storage account, and this has been presented at Build, has been able to reach 25 terabit per second in terms of egress and 15 terabit per second in terms of ingress. Last point before the conclusion, what is important also and changes in an AI training infrastructure is the importance of observability and monitoring, and how to remediate in case there is a failure. This because every time there is a single node failing that is compromising the whole AI training job, of course, you're losing important GPU time on the overall cluster and you are compromising the efficiency of your training. So in this scenario, of course, in the cloud, we have the classical way of monitoring infrastructure using Prometheus exporter, using Grafana dashboard, and basically collecting all the metrics for the nodes. We have ways to basically detect any anomaly inside these metrics, but at the same time, what is important is also having the first layer that you see here, the detection built inside the workflow scheduling, meaning that when, for example, in Kubernetes or in Slurm, there is the allocation of a job, there should be checks that before the job starts, really verify that all the nodes are healthy so that there is no disruption. And eventually, if there is a node failing, it should be isolated. And as a conclusion, after the node is isolated, it's very important that the node is also verified, and in a cloud provider like Azure, we have the possibility also to signal to the backend that the node is not healthy, and this basically will make the node not allocatable anymore. So a simple reboot of the node will bring up a new healthy node, which is something that, of course, it's a value added as compared to a typical on-prem infrastructure. So as a conclusion of the session, we would like just to say that there is a lot of HPC legacy that we are bringing with us when we approach the AI training, mainly because of the infrastructure competency and the infrastructure technology we built on top of that. AI training somehow can allow to modernize the way of how many things are being done, and this is an example that we see in many digital native companies. And the cloud is a good way to do that, because you can land in the cloud with your tooling with exactly the same elements that you usually use on premises, and then eventually decide, depending on your strategy and on the priority of your organization, to progressively modernize and introduce innovation steps inside your workflow. Thank you so much for your attention.
Thank you.